Very well. Now we can continue with our discussion about the Fourier transform. The Fourier transformation had one important property. It has a lot of important properties, but one of the important properties was that when you convolve two signals, the formula that you see on the top here, if you convolve two time signals, the corresponding Fourier transform of the convolution is obtained by multiplying individual Fourier transforms of each signal. X of t is Fourier transform and y of t is Fourier transform. So that's the convolution versus multiplication property, which tells us that whatever you have, maybe I should open a new page at this point. Whenever you have a new or an output which is related with the input in this format, continue from here, like x of t goes into h of t and the output is y of t. If you can determine y of j omega as something times x of j omega, this something is necessarily h of j omega, which is which can be related to h of t by the Fourier transform. So the Fourier transform of h of t is h of j omega, that is here. And the example that we saw the last hour was when y of t is equal to d by dt x of t. So the time derivative is the operation that the system is performing. It's a very simple differential equation input-output relation consisting of only the derivative. Then we see that y of j omega is equal to j omega times x of j omega. That was a property that we have proved before, which is indicating that this j omega is h of j omega. So this is the frequency response of the system, h of j omega, and it's equal to j omega analytically. Now let's see another example, quite trivial examples, and I have to confess that sometimes the trivial examples are more confusing because they are so easy that you start complicating things in your minds. And the situation is as follows. Again, a system is given with an impulse response to be equal to delta t minus t0. So the impulse response is delta t minus t0. What does this system do to any input which can be notated as x of t? Then how can you write y of t in terms of x of t? Can anybody tell me the answer here? Y of t is equal to, in terms of x of t?
xt minus t0.
Exactly, xt minus t0. Because it's a delay system. The impulse comes in and the delayed impulse goes out. Therefore, an input comes in and the delayed version of the input goes out at the output. So this is y of t is equal to x of t minus t0. Now we can consider this and one from here. Let me start from the left-hand side. In the left-hand side, I can see that h of j omega is equal to the Fourier transform of h of t. Let me first write it like this, which is, in the Fourier transform formula, delta t minus t0 e to the minus j omega t dt. This is the Fourier transform formula. And delta t minus t0 is appearing only at t is equal to t0, and all the other t values are multiplied by 0. All the other values corresponding to different t time instances except t0 will be equal to 0. So the integral, it actually depicts e to the j omega t only at t is equal to t0, and that makes e to the minus j omega t0. So let me go step by step. It's a repetition. We have done these things before. Delta t minus t0, e to the minus j omega t0 dt, because t is equal to t0 and nothing else, which makes this thing to become a constant and go out of the integration, and it becomes e to the minus j omega t0 integral of delta t minus t0 dt, which is the area under an impulse. It is a shifted impulse, okay, but whatever the area is underneath is still equal to 1. So the answer is e to the minus j omega t0. This was h of j omega. Okay, we found it by taking the Fourier transform of delta t minus t0. You can find the Fourier transform of delta t minus t0 in various ways. For example, the Fourier transform of delta t was 1, and you can apply the shifting property of delta t on delta t to make it delta t minus t0, and the Fourier transform of 1 will be multiplied by e to the minus j omega t0. So the output, again, h of j omega is therefore e to the minus j omega t0 times 1, which is this. So you can just determine it in various ways. The other one, we can take a look at the right-hand side of the arrow part, a different perspective. It's the same perspective, but from another point of view, maybe. Let's take the Fourier transform of both sides of the equation. The left-hand side will be y of j omega. The right-hand side will be the Fourier transform of x of t minus t0, which is a shifted version of x of t. So what is it? Using the shifting property, it is e to the minus j omega t0 times x of j omega, isn't it? Using the shifting property. Okay, so this is h of j omega, which is equal to e to the minus j omega t0. Clearly, these two are the same. Okay, you can look at the problem in various ways. Sometimes you relate the output into the input, like y of t is equal to x of t minus t0 to determine h of j omega. Sometimes you just think of it as h of t as the impulse response, and let me take the Fourier transform of that impulse response of h of t, and that is still the same thing. So these are just the same problem or the same question solved in different methods and giving you the same answers. Now, I will open a new page because I will talk about the dual property of convolution property. What was the convolution property saying? It was saying that if you convolve two time signals, you multiply their Fourier transforms in the Fourier domain. What happens in the other way around if you multiply in the time domain? So multiplication in time domain. Let us write it like this. R of t, you see now I'm using a different function terminology. It doesn't we don't have to fix into x of t, y of t, or f of t, g of t. It could be R of t perfectly well, is equal to s of t times p of t. So we have two signals, s of t and p of t, and I'm multiplying them. What is happening to their Fourier transforms? This property could be derived using duality. You remember the Fourier transform formula, if it looks like something like, if a time signal looks like a Fourier transform, then the Fourier transform looks like the time signal. That was the duality property, the cross similarities, you may remember. When you use that one, that duality property, you will find out that the Fourier transform of R of t, which is R of j omega, is equal to 1 over 2 pi, the Fourier transform of S, that is S of j omega, convolution with the Fourier transform of P of j omega. And the convolution is now on the frequency axis. So I'm convolving two functions, two signals, along the omega axis, okay? In the same way that I do convolution over time signals. Now I'm convolving frequency signals, and that's a possibility. And this is what is happening in the Fourier domain. The multiplication in time has one very significant application, and that is known as modulation. And this also gives you an idea about what you will see in the early weeks of the Introduction to Communications courses next semester. Because communications is done by modulation. And modulation and multiplication in terms of electronics are interchangeably used. Sometimes when people means multiplying, they say modulating. So I'm applying modulation. This is a modulation circuit, they say. So what is the modulation circuit doing? It is multiplying two signals. I have x of t and y of t, and the output is their multiplication. That is a modulation circuit. So in electronics, modulation and multiplication is used in an interchangeable manner. But modulation has also some telecommunications idea. It is the translation of, or the transformation of a baseband signal. By saying a baseband signal, I'm meaning some low frequency signal, like my speech or any audio signal, which is low frequency, band limited to 20 kilohertz maximum, okay? That audio signal, in order to transmit that into long distances through air or through space, what you have to do is you have to push the frequency content to a very high frequency, like megahertz, gigahertz, whatever. And over there, it can go at long distances and it won't be heard. I mean, people in between will not be aware of such high frequency modulated signals. But the radio receiver can demodulate that thing and pulling back that high pass or high frequency modulation waveform back to the low frequency and play it using the loudspeaker so that you're listening to the radio. That is the modulation concept. And the modulation is done, one modulation technique, which is a very fundamental one, is done by simply multiplying your baseband signal with a high frequency sinusoid, let's say cosine. So how does it work then? We have an S of t signal. I still cannot observe my eye. Okay, yeah, now it's coming. The S of j omega is the Fourier transform of S of t, and it's a low pass signal. So just as an easy illustration, I'm just going to use this triangular waveform. And let's see that the peak is A, and it is band limited between minus omega 1 and omega 1. Such signals are called baseband signals, and I'm going to transmit this signal, or the signal with this Fourier transform. I'm going to transmit it with P of t by multiplying with P of t, which is equal to cosine omega 0 t. So its Fourier transform is P of j omega is equal to, do you remember how to get the Fourier transform of sinusoids or periodic signals? By finding the Fourier series coefficients and inserting impulses at the corresponding frequencies of those Fourier series coefficients. What are the Fourier series coefficients? 1 over 2 at frequency omega 0 and 1 over 2 at frequency equals minus omega 0. So meanwhile, I'm just trying to draw these things. Like, let's say omega 0 is here, minus omega 0, and omega 0 is here. So this is P of j omega I'm drawing. So these two impulses, what are their magnitudes? They are equal to the Fourier series coefficient times 2 pi. So 1 over 2 times 2 pi is pi. And therefore, these two impulses have magnitudes of pi. Now I can write the P of j omega as pi pi times, in parentheses, delta omega minus omega 0, which is an impulse at omega 0, plus impulse at minus omega 0, which is this. All right. So this is P of j omega. And the left-hand side is S of j omega, which is a shape. But now we have to multiply S of t with P of t, which means we have to convolve S of j omega and P of j omega to obtain the convolution output, which will be denoted by R of j omega. That is equal to 1 over 2 pi from the formula. This 1 over 2 pi comes in. P of j omega convolution with S of j omega. So I have to convolve S and P on the frequency axis. How do we make the convolution with an impulse? That was a question that I asked in the first midterm. And in that question, it was something similar to this situation. We were convolving with impulses. There was a shape and there were two impulses. So the way to do the convolution is you have to shift this shape by the amount of the shift of the impulse separately for the right-hand sided impulse and for the left-hand sided impulse. So we will have, therefore, something like this. Two of these triangular waveforms. And one of them is around omega 0. The other one is around minus omega 0. This point is omega 0 minus omega 1. This is omega 0 plus omega 1. And conversely, this is minus omega 0 plus omega 1. And this is minus omega 0 minus omega 1. Okay? They are the boundaries of this triangle. What about, this is R of j omega. What about the peak value? This one. What is this point? Now, if you take a look at S of j omega and P of j omega peak values, one of them was A, and P of j omega impulse values were pi. So pi times A will be the peak value of the convolution, pi times A, and then I'm multiplying everything by 1 over 2 pi because after the convolution, once the convolution is done, I'm multiplying everything with a 1 over 2 pi in the formula that we see. So A times pi over 2 pi is the value, which is A over 2. A over 2. This is where R of j omega appears, A over 2. Now, this is called modulation because if omega 0 is a very high frequency, although I didn't draw it like that, I mean, I have drawn omega 0 at a very low frequency, but naturally, these things are like very far away from the center, and therefore we have some gaps here. Omega 0 is a lot larger than omega 1, okay? But I don't have that kind of a space here, so I'm just plotting it like this. This is what we call a modulation, and omega 0 is very high megahertz range frequency, and we cannot hear them, but they are in the air everywhere. We are just unable to perceive them using our ears, luckily and fortunately, because otherwise, if you could have a radio receiver in your head, that means you are receiving all types of information that has been transmitted, including the digital frequency modulations and everything. Fortunately, we don't hear that. Unfortunately, interestingly again, The poor animals called whales in the ocean, one larger class of whales, are capable of depicting, I think, short-wave communication or middle wave. I don't know, one of them. So, because they have a huge body size and their body size can resonate with the wavelength of this communication technique. So they hear a noise constantly. And people believe that maybe that's why they sometimes lose their ways and just hit to an island and they die over there, because they are unable to navigate under these noisy situations because of human telecommunications. I'm not sure about that, but that's a possibility. So this is how we communicate, but we communicate only on the modulation side. There is also a demodulation. I mean, your radio must do something. To convert this R of j omega back to S of j omega. S of j omega can be played on the radio loudspeaker, but R of j omega, it's very high frequency, you cannot play it. So the radio is doing something like this. One way of modulation. This is called double sideband modulation, by the way, because we are using both the positive frequencies and the negative frequencies. There are other ways of making communications. The demodulator first applies a filter around the desired radio station. So you tune to the station, which means you're first applying a bandpass filter around omega 0. That bandpass filter avoids us or avoids the contamination of other stations which are appearing at other central frequency, not this omega 0, but an omega 0 prime, for example, which is neighboring to that one. So this is not an isolated airspace. It's shared by a lot of radio transmission. Therefore, you have to use an empty slot. And that empty slot, you tune on your radio. So first we apply a bandpass filter, which will give you these two triangles, okay? And then you further multiply this R of t again with the same, exactly the same P of t, where P of t is, again, cosine omega 0 t. So you multiply the time signal by with P of t. So the demodulation is again another modulation. I'm modulating again. And what's happening over there? It causes, and this I am going to denote by S prime of t. It makes S prime of j omega to be equal to 1 over 2 pi times R of j omega convolution with P of j omega again. And P of j omega is this, okay, this again. I'm convolving my R of j omega with these two impulses once again. Then what does that make? It makes this. You have these two triangles, and these two triangles are, because of the two impulses, first shifted to the right by an amount of omega 0, and then shifted to the left by an amount of omega 0. So I will have two replicas of these triangles. One of them will be this. All right. And the other one, let me draw them with blue, green. The other one is this, the same triangle I am trying to draw, and this over there at the left. All right, so this is the signal, S prime of j omega. So we have two triangular shapes that exactly coincide in the center. This is S prime of j omega. And the black one will have a magnitude of a over 4, and the green one will also have a peak value of a over 4. This peak value is also a over 4. This is also a over 4. Okay? And two exactly the same triangles in the center will be added up because they are the same signals.
Hocam.
Yeah.
Bu merkezdeki üçgen nasıl oldu bu acaba?
Okay, this is at 0. This is omega 0. This is 2 omega 0. Notice that the top two triangles are at omega 0 and minus omega 0, and 0 is the center. Omega 0 here and minus omega 0 here, right? This is the shape. And I'm convolving this with these two impulses at the top. The convolution is still the same idea. I have these two triangles.
Tamamdır hocam.
And I'm shifting it to the right because of the right-hand side impulse over there. I'm shifting it to the right. And because of the left-hand side impulse over there, I'm also shifting it to the left. And the shift amounts are exactly the same as omega 0. So when I shift this minus omega 0 and omega 0 triangles to the right by omega 0, one of them will appear around 0, the other one will appear around 2 omega 0, the black ones. And when I shift it to the left, then the green ones will appear. One of them will be around 0, the other one will be around minus 2 omega 0. This is minus omega 0. Okay? They just coincide around the DC. And that coincidence will make, and by the way, I will also apply a low pass filter because I really don't want these extremely high frequency components. They are inaudible anyway. Okay, your speakers cannot play them. They are at 2 omega 0. So it's even more than the modulation frequency, twice the modulation frequency. But around omega 0, around 0 frequency, I apply a low pass filter, the dashed low pass filter, and it will make twice of the triangle with a peak of a over 2 from minus omega 1 to omega 1. And then I play it. So the demodulation is also obtained by modulation again, another multiplication with exactly the same, at exactly the same frequency. Okay, this is called double sideband modulation. And there is no carrier, only the signal is over there. So in the next semester, you will notice that the modulation and demodulation technique for this thing is called double sideband suppressed carrier. Because unfortunately, modulation also requires a carrier to appear somehow. So you have to suppress it to make this thing. That's an electronics detail, but the name is coming from electronics anyway, and it is called double sideband suppressed carrier. So in telecommunications, this multiplication thing is used. Multiplication in time, the top equation, will make convolution in frequency. All right. Now, I will, so much about these properties, a good time to proceed to the linear time invariant systems and linear set of differential equations. That is the differential equation which makes the linear time invariant system, which formulates the LTI system, and how to convert them into frequency response and correspondingly the impulse response. For instance, I may start from an example. Okay, let me put it like this: d by dt y of t plus a times y of t is equal to x of t. Now, this is a constant coefficient differential equation it's a first order differential equation. It could be second, third, whatever order. But since it's a differential equation, it corresponds to a linear and time invariant system. And if you put a plus b here, then it becomes not a linear and time invariant system anymore. So LTI systems must have y and x at the left-hand side and the right-hand side of the equation and their derivatives, etc. So this is the constant coefficient linear set of a differential equation, and it corresponds to an LTI system. When you look at it, you don't have to apply any checks of whether it's a linear or time invariant or whatever. That may be hard for differential equations, but I'm just telling you that it's an LTI system. But the question is now a difficult one. It's given in this form, and what is the impulse response? This is a very fundamental problem, a very fundamental question also. And the opposite is also true. I may give you an impulse response, h of t, and I can ask you, what is the differential equation which relates the input to the output? The first line of the differential equation is an input-output relation. Now I'm asking you, what is the impulse response? And there is no direct way of formulating the impulse response, h of t. There is an indirect way, and that is through the Fourier transform. What we do is, so the answer is, we take the Fourier transform of the equation, the input-output equation or the differential equation. What is it? The Fourier transform of d by dt y of t. What is it? It is j omega y of j omega. That's the property, right? We've learned it. If you take the derivative of a signal in the Fourier domain, you multiply it with j omega. That's it. Plus a times y of t. What is the Fourier transform? It's easy. It's a times y of j omega. And the right-hand side is the Fourier transform of x of t. Or it could be a little bit more complicated, but now it's easy. It's x of j omega. All right. Now we are in a very good situation because I can put everything on the left-hand side of the equation into a parenthesis of y of j omega. And that is j omega plus a. And that is equal to x of j omega. And y of j omega divided by x of j omega is, what is this, by the way? By definition, y of j omega is h of j omega times x of j omega. Therefore, y of j omega over x of j omega is h of j omega, the frequency response. And from the previous line of the equation, y of j omega over x of j omega is equal to 1 over j omega plus a, or a plus j omega. Okay, this is h of j omega. Can you tell me the inverse Fourier transform of this just by inspection? Because we have seen this Fourier transform before. Yeah, e to the minus at u of t, exactly. Doğukan. We did it. We solved it. And how did we find it? We found by taking the Fourier transform of the differential equation. That's a trick that we are going to use in for longer differential equations too. As long as you have a differential equation, you can always apply this useful trick. Another example. Of course, sometimes they tend to be a little bit more difficult, but nonetheless, it's all manageable. You can always come up with h of j omega at least. You can find it. And in many cases, if you have h of j omega, you should be able to find the inverse Fourier transform using some properties, looking at the tables, etc. The second derivative of y of t plus 4 times the first derivative of y of t plus 3 times y of t is equal to d by dt x of t plus 2 times x of t. So this is also a differential equation, and as you see, there is no constant coefficient or constant value in an additional form. It should be avoided because it spoils the linearity. The linearity must have a zero input, zero output situation. And if you have a plus b or something like that in either side of the equation, then x of t, when x of t is 0, the output will not be equal to 0 anymore. So that's not allowed. These are the differential equations that you have. And then you take the Fourier transform of both sides of the equation. We haven't seen how to take the Fourier transform of the second derivative, but it's easy. The first derivative is multiplication by j omega. The second derivative is multiplication with j omega again. So j omega squared, for instance, times y of j omega plus 4j omega y of j omega plus 3y of j omega is equal to j omega x of j omega plus 2x of j omega. Now it's a longer expression, but the left-hand side and the right-hand side of the equations can be put into parentheses of y j omega and x j omega. Let's do it. Y j omega in parentheses j omega square plus 4 j omega plus 3 is equal to x j omega in parentheses j omega plus 2 and y of j omega over x of j omega, which is h of j omega. You see, this can only be written in the frequency domain. You cannot write it in time domain. Y of t over x of t is not h of t, okay? Because y of t is x of t convolution with h of t. But in frequency domain, they are in the multiplicative form. That's why we can have it in the Fourier domain. This is equal to, therefore, j omega plus 2 divided by j omega square plus 4j omega plus 2. Now, you can say that j omega is equal to something. Let's say j omega is equal to s, for instance. Like you can write it like s plus 2 over plus, excuse me, thanks for the correction. In the denominator, it's not a plus 2. The final term is plus 3, of course. Okay, so sorry about that. S plus 2 divided by s square plus 4s plus 3 plus 3. Now, this is in a form which we are not familiar. We don't have this kind of Fourier transform this way or this way, whatever. S is equal to j omega. I'm just trying to write it in a short manner. It's not in a familiar form, so we have to put it in a familiar form. And for that, I should better find the roots of the denominator polynomial, j omega square plus 4j omega plus 3. And what are the roots of those things? How can I split this into a form, into an addition of two forms? One of them is also a first order. The other one is also a first order, but those first orders are corresponding to the roots. And by inspection, I can find that this can be written as like j omega plus 1, something over j omega plus 1 plus something over j omega plus 3. Because if I multiply j omega plus 1 by j omega plus 3, I will get j omega square plus 4j omega plus 3. Okay, these denominator multiplication will give you that. And when you equate the denominators, this is the denominator that you will get. But I don't know for the time being what is, for instance, the top of this one, A, and the top of this one. I can call them A and B. So I need to find A and B. That's how I'm explaining you how I solve this question. Sometimes some students, yeah, for example, Salihcan already told me that 1 over 2, that which is the correct answer, by the way, but I cannot do that by inspection. I usually have to apply this and find A and B separately. From here, I write the equation as AJ omega plus 3A plus BJ omega plus B, okay, is equal to J omega plus 2. I'm sorry for these messes. J omega plus 2. So it gives me these two equations, A plus B, from AJ omega plus BJ omega is equal to J omega. A plus B is 1. And 3A plus B is equal to 2. So I have to solve for this. And when I do that, I subtract the first equation from the from the second one, and I say 2A is equal to 1 and A is equal to 1 over 2, and therefore B is also equal to 1 over 2. So I write this to be equal to 1 over 2 over J omega plus 1 plus 1 over 2 over J omega plus 3. So this is the frequency response, H of J omega. I just simplified it into first order format, because from first order, I know the Fourier, inverse Fourier transform. For example, the first one, the inverse Fourier transform of the first one is 1 over 2 e to the minus, there's no J, excuse me, minus 1 times t, minus t u of t. And this one is, again, with a 1 over 2 e to the minus 3t u of t. So I have to add them because their Fourier transforms are added. Their time domain versions must also be added. And this is h of t. So I found it again. So in an examination, if you encounter another situation where this time it is not second order but third order, then what does it make? It just makes a more difficult question because the denominator polynomial in terms of j omega will not be second order like this one anymore, but it will be third order. So you have to somehow try to split it into first order as much as possible, except a second order remaining thing can also appear, which corresponds to the Fourier transform of e to the minus a times absolute value of t without the u of t. From the tables, just check that for one particular case of a second order system, that is the result. There was a question around the transfer function oluyor değil mi? It's the impulse response I'm finding. Okay, I found h of t, which is the impulse response, and h of j omega, which is this one or this one, where they are the same. That is the frequency response. So h of j omega is the frequency response. H of t is the impulse response. Transfer function is related to the frequency response, h of j omega, but with a difference. Instead of h of j omega, you have to say it as h of s. That's why I was using s instead of j omega. We will see it. It appears in Laplace transform, which is the same as the Fourier transform in most practical purposes. Just j omega is s, okay? Laplace transform hint from now. So let's not call it a transfer function, but let's call it a frequency response if you're talking about h of j omega, and let's say it impulse response if you're saying h of t. And the last thing that I found in the box, it is not a transfer function, it is an impulse response, which corresponds to this differential equation. This is the input-output relation. The others are impulse responses and frequency responses. This is critical. This last part is critical, and I'm particularly fond of asking questions related to the determination of the frequency response or the impulse response, and sometimes vice versa. So we have three things, three entities. Let's write them. One of them is the frequency response. It's here. We have impulse response here, and we have a differential equation here. Okay. And I can give you one of them and ask you another of them. And all of them are related to the frequency response. So I can give you the frequency response and ask you the impulse response. Then what you have to do is you have to find the inverse Fourier transform. I can give you the frequency response and ask you the differential equation. Then what will you do? You have to invert the operations that we did. Because you see, this is h of j omega over here. You just write h of j omega expression as y of j omega over x of j omega and make the cross multiplications and come up with this, and then finally take the inverse Fourier transform to convert everything into this format, which is the differential equation. So I can give you the frequency response and ask you the differential equation of the linear and time invariant system. But a better question would be to give you the impulse response h of t and ask the differential equation. Then what you have to do is just to go all the way backwards. From h of t, first you find h of j omega. And from h of j omega, you say h of j omega is y j omega divided by x j omega. Make cross multiplications, write them in the form of an equation, and take the inverse Fourier transform of that expression to come up with the differential equation. Okay, which is the reverse operation of this particular example. That could also be a question. Okay, now this essentially concludes the continuous time Fourier transform discussion. There are several properties, there are several questions, and there are several indefinitely many variations of questions that could be asked, including the ones in the book. So I strongly recommend that you do some exercises, okay, before coming to the final examination. Try to solve questions, but the concepts are here, and that's all I want to talk about at this point. So it may be a good time to give a break of 15 minutes. So at 3:05, 15:05, we will meet again, and we will start this time the discrete time Fourier transform, which is related to the discrete time Fourier series, of course. And we will continue with a few properties and examples from there on. So I'm stopping the recording now. If you have any questions, you may ask. Let me wait for a few seconds if you have any questions. Otherwise, I'm stopping the recording, and I will come back at 3:05. So let's meet then.